Good evening here and good afternoon in India and good morning to Dr. Sachin Shah and to maybe good night to some participants from West Indies. So on behalf of the organizing committee, we feel very happy to welcome Dr. Sachin Shah, Associate Professor, Department of Mathematics and Statistical Sciences, Botswana International University of Science and Technology, Botswana, to the third day, last session of this international workshop on advanced finite element method, guessing and coding. So in this, Professor Sachin Shah is going to give the talk. In this talk, he told me that he is going to introduce how we can do finite element solution procedure using the software. Professor Sachin Shah has obtained his PhD degree from Indian Institute of Technology, Kharagpur in the year 2010. He obtained his MSc also from IIT Kharagpur. He is a life member for various mathematical societies. He got postdoctoral fellowship. He did his postdoc at the University of KwaZulu-Natal, South Africa, from 2012 to 2014. Prior to that, he worked as an assistant professor, grade 2, at Department of Mathematics, School of Applied Sciences, KIIT University, India. After his postdoc, he got appointed at Botswana International University of Science and Technology, Botswana, as a senior lecturer. Thereafter, from the year 2020, June, he promoted to associate professor and working in the university, Botswana International University of Science and Technology, Botswana. Professor Sachin Shah has published several papers. Many got published in Q1 journal, and some of his interesting papers got published in the journals like Journal of Magnetism and Magnetic Materials, Nonlinear Dynamics, Thermal Science and Engineering Progress, Alexandria Engineering Journal, Journal of Radiation Research and Applied Sciences, and many other good journals he published. The publication list, it is like very long, about 100 papers we can see in his publication. So he has completed 2 funded projects in the currency BWP 150,000 worth. Sponsored agency is Botswana International University of Science and Technology. And another project for 14 lakh by CSIR. These 2 projects he has completed, and he has supervised 2 PhD students as a main supervisor and 2 more as co-supervisor. And he has guided several MSc theses, and he chaired many conferences. He has been the examiner for various PhD and master examinations. He has 4 books for his credit. He has been served as an invited speaker, guest speaker, keynote speaker for several conferences of international repute which are organized worldwide. He also published several conference proceedings. Such an interesting expert is with us today to deliver his talk on the topic finite element method for solving boundary value problems. So, Professor Sachin Shah, we are really thankful to you for your time and effort to join this workshop as a speaker and enlighten the participants in terms of the coding point of view. Over to you, sir.
I think I am audible now.
Yes, sir, you are audible.
Yes. Thank you very much, Prof. Sivraj, for the introduce me. And I am actually very much happy to give my lecture in this workshop, mainly with the students and obviously the faculty members, everyone is there. Uh, Let I start the things. First of all, good afternoon to all. I see that last, sorry, is a problem. Is everything is fine? Okay.
Yes, sir, everything is fine, sir. Your video is clear, voice is clear, and slides are movable. Everything is fine, sir.
Okay. So, good afternoon to everyone. I see the last today's lecture, and I see there people are talking about finite element in a very depth, even the discretization and everything has done. So here I mainly focus on a few ideas like that, how we are using this finite element method to solving the boundary layer flow problem, which is very basic ideas and very basic for fluid mechanics. Those are working on these directions. We know that boundary layer flow problems. And when we start this talk, we mainly focused on the basic ideas like that motivation for finite element method, understand how it is differ from the other numerical techniques. And we try to derive some formulation and then apply first for the most common equation, which is the Blasius equation, but we try to modify it a little bit using the magnetic force. And after that, we try to put or include the temperature equation in that Blasius equation. And we try to see that how to write the code step by step, because these are the small equations. So if we are able to understand the writing process, then maybe we can do the same for the big equations. Obviously, we can go for some future ideas that how we are implement this finite element method in different boundary layer flow problems. And finally, we can go for some conclusion part. Obviously, a portion will be there related to question answer, and I am happy to see the people's interested in this field. So if we're talking about the finite element method, we are know that this is one of the powerful numerical techniques. In general, when we are try to solve the problems, or maybe when we choose some realistic problems, that realistic problems we try to write in a PDE's forms, ODE or PDE form. So when it is coming as a differential equation form, it is very difficult for us to solve the analytically for some cases. So that means in that case, you need to using some numerical techniques. And finite element method is one of the very powerful numerical technique which approximate solve any kind of boundary value problems, mainly when it is involved the partial derivatives. So this is effective for the problems when you have the very complex geometry. And sometimes we are using complicated boundary conditions. Also, it is very useful when you have the coupling physics and some other external forces in your governing equations. This finite element method is hugely used in structural mechanics, heat transfer, fluid dynamics. Even when we'll go for some application orient to that one, that means biomedical engineering, and those cases, it has a huge applications. Mainly when you have a complex geometry or irregular geometries. Among the different numerical techniques, we mainly familiar with the finite difference method. But I told you this finite element method is much structured, more convenience than the finite difference method. And the main reason for that one, you can easily generate different geometry in the finite difference element method. And those can easily fit with the irregular domain or the curve boundaries. And it also allows the local mesh refinement and mainly support the higher order approximations. So the basic ideas I see earlier, the authors or speakers, they are talking about many basic ideas of this finite element. And I know you are aware of that. So I am not going for more depth here. Only I can say that general, the main basic ideas are that it can easily divide the domain into small elements. And you can easily change the shape, change the density of the elements or the number of elements you can easily change. It depends on that where your flow field is more impactful, whereas this is less impactful. This also allows us to assemble the global systems, and it by default help us to solve different unknowns or the parameters where we are interested for. So as I told that when we are talking about the finite any realistic problem, we end with some differential equation form. It may be ODEs, it may be PDEs. So generally, this differential equation form, we can written like that way, LU equals to F form. And we can choose a boundary, which is the del delta, where we can incorporate different conditions. Generally, boundary conditions, we are familiar with Dirichlet's, Newman, and also mixed type boundary conditions. As an example, we can say this one-dimensional Poisson equation. If you see this equation, this is the one-dimensional Poisson equations, and this is a simple equation form d2u dx2 equals to fx, a simple ODE, and these are the two conditions are here. So this is one examples of this PDs. And when we are getting these equations, after that, we'll go for the weak formulation. That means we try to introduce or write as a AUV equals to LV form, where V is a suitable function in the space and A is the bilinear form. This is depends on how many equations are there. And based on that, we are trying to fit the weak formulations. And after that, we try to include the elements. Obviously, we had different type of elements are here. You can go for linear elements or quadratic elements and so on. This is based on the problem, how you can choose your elements are there. So we go for the discretization, approximate V as a finite dimension of a subspace VH, and you have the basic function phi I, so that your UH we written as a F function of, in previous equation we written L is a function of U. So U can be written like this way, UH in this form, and which basically end with a linear system of equation AU equals to F. And our target is that solve this equation and get the solution. So when you are getting the solution, and then after that, you see what is the error procedure, or you can find out your residual. When you find the residual, obviously our target is to small the residual so that you are getting more accuracy. And obviously this residual, how you define that one, that also depends on the mesh size and polynomial degree of the basis. Based on that, you try to simplify and you try to reduce your residual. to get a proper convergence. As I told that, we had different shape function. You can see here, we can define this type of shape. One is the linear shape function, which you can define like that way. Here the element is y1 to y2, and phi 1 y is in like that way. Phi y2 is this one, and h is the element size, that is yk plus 1 minus yk. Most of the cases, we are familiar to use this linear shape function because this is very simple to implement and efficient for the smooth problems. That means if your geometry is very simple, then it is better to go for the linear rather than the other elements because it is very easy to handle the things. But they had the limitation like that the lower occurrence. That means you are not getting the proper convergence some cases if you have the complex geometry. And sometimes it is not actually capture the boundary layer unless mesh is refined. So these are two limitations are there. And if that is the case, obviously we'll go for the higher shape functions like that, the quadratic one, where we are using the 3 nodes per element, 2 end nodes, and one is the midpoint. And here, these are the way how we can define this phi 1 xi, phi 2 xi, and phi 3 xi. These are the 3 elements defined in the quadratic shape function. And the advantage of this one is that it is easily approximate the curvature. If your geometry is a curve, then it is easily capture the things. And second one is it is useful for capture boundary layer behavior more accurately. So you can see in this table, we had different shape functions, linear, quadratic, cubic, and so on. So they have some advantage and drawbacks also there, because when you will go for the more elements or shaper, then your coding is more complicated and also it is time taking. But obviously, you will get more refined values and it is converge much faster. Now, our main interest is that how we are using this finite element method. And here I try to explain this finite element method used for the boundary layer flow. So some of have those mainly doing fluid mechanics. They have the idea about the boundary layer flow. That means you can say in a sense that suppose this is the boundary. This is the boundary, we know it that, and then the flow is coming like this way. So close to the boundary, it will get a layer, which basically the region of the disturbance. So here you will get the more disturbance of the fluid, but obviously when you go beyond the layer, here you will get the less disturbance or no disturbance at all. So that means the region which we are interested to study is this region, because here the fluctuation is more, the changes are there. And generally here u is a function of y fall velocity, because x direction is the along the plate and y is the upward. And this the y direction fluctuation is more impactful here. So this is a simple boundary layer concept where you have the disturbance or your equations mainly focus on the or close to the boundary. And after a certain boundary, you will get the same free stream velocity or ambient velocity. So this initial velocity is your V naught. And when it is attached with the boundary, then your velocity is now 0 because the plate is the stationary. And they create a small layer here. And beyond that layer, when you will out from here, your velocity again the same as your free stream velocity or ambient velocity. This thickness of the boundary layer, it is based on the, I can say this is the V naught, based on the what is the velocity you have. So this is the normal boundary layer concept, but obviously we are interested to reduce that one or write that one in an equation format. I need to go some assumptions are there. One is close to the boundary. So greater than 1, and the boundary layer is very thick, and that is very much less than the length of the plate. So when you are using these conditions, you can simplify the things and you will come with some simple equations. So here we written the general continuity equation, x momentum equation, and y momentum equation for two-dimensional, steady, two-dimensional, and incompressible flow. So this is the general equation, but when we are using these conditions are there, then these equations will be simplified and it can be written like this way. This is the final equation form. This comma del p del y is 0. So this is the final equation form, what we are getting there. I think some sign is not coming, but this is like that. So this is your final boundary equation or boundary layer flow equation. And the conditions, it is based on the problems, how you can define. Since we are consider here a horizontal plate, which is a fixed, so that's why we have considered here no slip condition. That means the velocities are 0. And we know that after the boundary, you have velocity. So that means when y tends to infinity, you will get ambient velocity u infinity. So these are the conditions we can implement in this boundary layer problem. As I told that, you can later on modify these equations based on your geometry, based on your what you are considered here. So the most common equations of the boundary layer is the Blasius equation. And you can see here these equations. These are the continuity equation for, and this is the momentum equation. This is a steady, that means independent of time, incompressible, that means the density is constant, and two-dimensional laminar flow. And this flow is over a semi-infinite flat plate, as you see this geometry. So this is the equation, what is the simple and general form of the boundary layer problem. Now, here, as I told that we are interested to now solve, when you get some equations, our interested to solve this equation using the methodology. So in this equation, with this Blasius equation, I additionally add term. So if you use this magnetic term, the equations is become like this. Now we are interested to solve this problem finite element method. So obviously when we try to solve this finite element method, first we try to, or interest, right? That means how to generate the weak formulation, how to generate or how to introduce the shape functions, those things. So first we study those ideas, then we'll see how to write the code using those ideas. So hope you can get my handwriting. So our first work is that we try to go for this weak formulation. Let me know if you not understand the things. So that means we go for some 0 to L form, because we are considered here L is the thing. So it is like that mu d2u dy2 minus sigma beta naught square u plus rho u du dy. With that, obviously, what we need to do? We are using a function v or phi, anything you can use here, dy, right? This is called the, yes, which function this one?
Which function?
This phi y, what I had written here. We are going for the weak formulation, right? Okay, let's say this is called the test function, right? Okay, now what we will do, we try to simplify these integrations, and we can write this one, maybe the first term we can as a, because here we are using, let I make it clear. Let's write as a Vy to make it the things clear. Okay. So now we are using the integrations, and when you are using the integrations, you will get like that way 0 to L mu du dy dv dy of dy plus you get mu du dy v, your limit is 0 to L, and the other two are as usual, there is no change. This is uv dy, your limit is 0 to L, plus rho u du dy v dy equals to 0, which you can simplify it as a, like this way. You can say this is a of uv minus n uv, this equals to 0, 4, right? Where you can say your a uv is this one, which is mu 0 to L u dash v dash dy, and you consider the sigma here, that means the magnetic part, uv is 0 to L dy, and n you can retain as the nonlinear term. N is represent the nonlinear term, which is basically rho u dash v dy. Limit is same, 0 to L. So this is the weak formulation we get here. So after the weak formulation, our next is that how to implement this AFEM approximation there. So when we go for this AFEM approximation, we retain this uy, which is our velocity profile. This is approximate as a, let's say z equals to 1 to n, because we try to split into the element form, maybe uj phi j y form, right? Where this phi j is basically this, our function. You may consider the linear shape function, you may consider the quadratic shape function. That is completely depends on the problem. So phi j y is here, this let we consider the linear shape. So this is piecewise linear shape. And Ui or Uj is basically our unknown nodal points, which we need to find out, or nodal values. And n is basically our number of elements. So now what we will do, now we are using this phi. We know that phi is the linear here, so we can say phi I, or maybe let's say phi 1 and phi 2 form, because we had two elements for the linear case. This is yi plus 1 minus y by h. H is the space between two elements. And phi 2 we can written as a y minus yi by h, right? So when you are finding the derivatives, phi 1 dash, you will get simply 1 by h. And phi 2 dash, you will get 1 by h, right? So what is h? H is basically the element size, yi minus 1 minus yi. Now we are using this concept here to discretize the things. So now we will go for the discretization. Oh, let I go for does anything happen? Yeah. So now we'll go for the things. So when we'll go for the discretization, so first our diffusion term. What was our diffusion term? So our diffusion term is here yi plus 1 mu. U we written like that way. So what is du dy? That is as a d phi I dy. And you have d phi j dy, obviously in integration form. Now, since we had two elements here, phi 1 and phi 2, so we just try to see those elements. And when we are put the values here, you basically get a 2 by 2 matrix, which like this way, 1, minus 1, minus 1, 1, right? This is, let's say, this one as a KE. This is the diffusion term. Now, for this magnetic term, that means sigma beta naught square part is there. So this is, you have yi plus 1, y1 element, phi 2, 1, 2. This basically gives you again a 2 by 2 matrix. And that you will get. The main challenge is that how to control this or how to deal with the nonlinear term, which is a very important or challenging things for the finite element method. So we have the nonlinear term. If you go for the main equation, you can say that is like that u du dy. This is the nonlinear term we had. So here, this is the velocity u, y. As we consider that one, this is equals to ui phi I in summation form. And here we had the linear elements, so that is 1 to 2. So this you can retain as a u1 phi 1y plus u2 phi 2y, right? So now when we are deals with this nonlinear equations, from here let I write some points. So U1 basically corresponding to UI, U2 basically corresponding to UI plus 1. That means continuous two elements. So du dy basically the derivative, but you can generalize this one as a simple gradient formula. That means U2 minus U1 by the difference between them, which is H. This is general derivative definitions we are using for du dy. So when you're done with this, then you go for actual this nonlinear term, and this can be written as a yi 2yi plus 1 rho uy du dy, and you are getting this phi iy, which is the test element or function, shape function here. So now if you simplify, you will get rho u2 minus u1 by h, which is basically a representation of du dy. And then you will get the integration yi plus 1. This ui, we see that this ui can written like that way. This is u1 phi 1 plus u2 phi 2, then phi I dy. So now here you are getting the combination like that when you deal with this one, phi 1 phi 1, phi 1 phi 2. Similarly here you will get phi 2 phi 1, phi 2 phi 2. So that means if we know those integrations, then we had done with the things. And those are easy. If you see the integration for phi 1 phi 2 or phi 1 phi 1, you can do yourself also this one. You will get h by 3. And if you integrate phi 1 phi 2, you will get h by 6, and so on. You can do the remaining one also. So from here, we'll get, since we had two elements, elements of two nodes, so each node we can find out what is the nonlinear term. So if you go for the first node is node 1, you can say any E, this is equals to, you will get rho U2 minus U1 by H, which is by default there. Now here you will get phi 1 and phi 1 phi 2. So that means U1 phi 1 is H by 3 plus U2 phi 1 phi 2, you will get H by 6. So that means you will get rho U2 minus U1 by H into H by 6. We just try to simplify to U1 by plus U2. And similarly, you can get for the second node. And this one, in similar way, the first term is fixed. That means this one is the same for all cases. Now here, if you take the common H by 6, you will get U1 plus 2U2. So that means the final NE, which is the nonlinear term, you can retain as a U2 minus rho U2 minus U1 by H into H by 6 to U1 plus U2, U1 plus 2U2. So this is, you will get a matrix of 1 by 2 row versus column, 1 by 2 matrix, right? So this is what the discretization you will get here. So maybe I do the same thing here. You can slowly go one by one. You will get the ideas here in this slide form. So this is what we are getting here. Here we consider the W, and in their phi, so same thing. So when you try to simplify the things, you will get three matrices here. One is the A, which is basically related to the is the problem. Yes, A is related to the stiffness matrix. That means this is the diffusion term, what we had here. And then you are getting M matrix, which is depends on the magnetic force. And then you are getting the nonlinear term, right? And this is the pattern of the matrix, what you are getting here, as I show you how you are getting the things. And when you are get this all things, after that, it is easy to implement in the code. But as we know that when we are using these numerical techniques, we are concentrate on also the convergence conditions. So if you have a good convergence, that means your numerical techniques is okay, and whatever the graphs you are getting, that is well defined and it's fine. So that's why this is necessary to estimate the error, and from that error, we try to minimize that error to get the convergence criteria. So these things are the steps what we are do one by one, and get the or solve the problem using the finite element method. Let now I go for the code and try to show you how you write the code and get the things there. Tried to open, where is that MATLAB? It's difficult. Oh, it's here. Okay. I hope it will connect quickly. It's given problem. Are you getting the? Have you seen the MATLAB?
Yes, sir.
Okay, that's great. That's why I entered both sides. So later, now here we are interested to write the code for that one. So what is our code? Our code is very simple, that we are interested to solve the Blasius equation, which is, or Blasius equation with magnetic parameter, right? Let I increase the size. I think it is well visible. So what is our equations here? Our equations is our mu, right? d2u by dy2 minus, we had the sigma beta 0 square or beta naught square u plus rho u du by dy. Is this okay? Let me see. Okay. Okay. Right. Sorry. Yeah. Okay. Du dy. Right. So what is our main target? First, we will see what are the unknowns are there. First, we put the value. Let's say we can write mu equals to 1, maybe rho equal to 1. Just put some random value. Sigma equals to maybe 1. Then your B naught, let's say this is B naught equals to 1. L, maybe we can say that the eta value is hanger. Eta value maybe we can consider as a phi. Why this? Yeah. L value you can consider as a phi. and U infinity, we can consider U infinity as a 1, right? These are the things. Now we can go for the AFEM discretization. Okay. So in AFEM discretization, we need to talk about the elements. How many elements you can consider? Let's say we consider 100 elements here. So the element size H should be L by L, right? Because L is the length of the total length of the, maybe I can say, boundary layer. So divided by N. And this nodes you can easily define with the line space, which is 0 to L. And we had the number of element is N plus 1 form, right? So this is the AFEM discretization. Then we can define the constants. What are the constants here? Yeah, constant matrix. Sorry, defined the constant matrix. And we can see here, we deals with stiffness matrix, which is basically we written as a KE. And we see that this is a 2 by 2 matrix, right? And if you remember the things, it is related to mu by H. This is multiply with, what is the matrix value? 1, minus 1, and minus 1, 1. This is what the matrix we have here, right? So this is our stiffness matrix. Then we will go for the matrix which is related to the magnetic parameters, which is ME. And this is like a sigma into B naught, obviously the square is there, into H by 6. And then we have the matrix which is 2, 1, 1, 2, right? So this is, I can say, local mass matrix. Okay. Now we can go for this system of linear equations form. So that means we assemble the things. So let assemble A and M, these two matrix. And for that, we can go for the element wise. So let's say for E equals to 1 to N, we can put the elements here. I dx is equals to the element side I plus 1. So here we consider E. So E plus 1. Then the A matrix we can create as a I dx. I dx equals to A I dx I dx, and that is add with Ke, which is the index matrix. Yeah, sorry, stiffness matrix. And then we create M, which is I dx comma I dx. And this is equals to M plus ME. That means we are assemble the matrix with the loop, right? And most of the time when we are introduce the matrix like this way, we can initially define the things, the initial definition. And the best way to consider the zeros. So A is zeros of N plus 1 matrix, and M also is the same as a zeros of N plus 1. So this is the end of our, we already create the matrix. Now we can go for the initial guess. That means we start with the initial conditions, what we have here, or initial guess here. So let's go for the initial guess. And we can consider as a capital U is equals to line space 0, U infinity, which already we have defined the value, n plus 1. So this is at the initial guess. And here, when we are using the finite element method, obviously we know that we are going to use this Newton-Raphson iteration. During this iteration, we'll check the convergence criteria, and when it satisfies the convergence criteria, after that we display the items in a figure form or graphical representation. So that's why these things are very important to introduce the Newton-Raphson iteration and try to understand the convergence criteria. So there are two ways to introduce the convergence criteria. One is that you can go for the maximum iteration, and second one is your tolerance. So let we put those both criteria so that which one satisfy first, they can end there. So here we can go for the maximum iteration, let's say as 50, and we see the tolerance, let's say 10 to the power minus 8. So this is the tolerance we have considered here. Now we will go for the main problem, that is the iteration 1 to maximum iteration. And then we will written as a R, which is the residual basically, is equals to A into U plus M into U. But only the things what we had not included here, if you remember that we had the nonlinear terms also. So we have not yet included here. So we can try to write this nonlinear convection term. So we just go for a simple function. So here we are interested for introduce this nonlinear convection term. And if you remember that, that is U du by dy. So let's try to write in a function form. Let we say function. Let's say NC nonlinear term. NC function nonlinear term equals to, let's say, nonlinear, let's say convection term. And what we need here, we need the velocity here, number of nodes here, and it is attached with rho. So rho we need, because if you remember that the term is rho into U du by dy. Oh, this is y.
Excuse me, sir. Can I ask a question?
Yes, please.
The max iteration, should that be underscore or should that be a minus? Right under the Newton-Raphson.
Yes, that should be underscore. Sorry, that should be. Even in MATLAB also, when you try to combine the things, minus means they directly take the algebraic operation. So that's why the underscores, if you big terms are there, you write is this underscore form, that if you see U infinity, U underscore infinity, and so on. Thank you.
Sir.
Yes.
No problem.
So nonlinear convection term we'll get here. Then we'll define the things one by one. Let's say N is basically the length, GTH, length of capital U, minus 1. We just try to make it consistent. This one, we can consider the zeros at the initial stage. And then we try to implement or generate the things. So E is from 1 to N. H, we know that the space of 2 points. So this is space between nodes E plus 1 minus nodes E. Then we can define E1, which is basically UE. And we can say U2, which is basically UE plus 1. And we know du dx, we have seen that one. That is du by dy, which we generally consider as a u2 minus u1 by h. Right? So then we will go for the main ideas. That means from the integration, what we are getting there. So we can put this value is equals to rho into du dx, which is basically du dy form. That multiply with h by 6. If you remember that matrix, that is a first row 1 by 2 matrix. So if you see the elements was 2u1 plus u2, that is one element. Another element was u1 plus 2 into u2. So these are the elements which consider as a val or value. And this one we can continue in the loop and try to generate the whole nonlinear convection matrix. So that's why we can write as a NC E plus 1. This equal to, you can say NC E plus 1. Sorry, this is E plus 1, the modified one. NC plus 1. So it is inbuilt there, and this value will generate the things. So we can put end, both cases, right? So this is the nonlinear term we had. So now we are interested to put this nonlinear term here, which is nonlinear convection term in this format. So that we are incorporate here. So we are getting this plus our nonlinear term, nonlinear underscore convection term, which is based on u, nodes, whatever you have. And we have a rho, which is the density term. Here we also introduce the Jacobian because we need to find out the residuals, and from there we need to see how the things are going on. So residual we had done. Now we go for the Jacobian, which basically we include to find the final solution, because here you are getting the total things in matrix form. So Jacobian is important here, and that is based on the stiffness matrix due to the magnetic parameter, and our nonlinear due to the nonlinear term. So first one is basically help you to find the residual, which basically the conditions we are going to use there. And second one is the Jacobian, which help us to find out the final solution. So Jacobian, U, nodes, and rho. So this Jacobian for nonlinear case, for linear case, it is very easy to find the Jacobian, but nonlinear case, it is difficult. And if you see again, we put a function here. So that means this is the second function we again need to find out. So second function is here, the Jacobian for nonlinear term. So our function, again, we can write the same way. Jacobian is Jn, and this is what the format, right? So same way we can go for n is the length and these are will be the same. N is the same, and in place of NC we had the JN here. Remaining everything is same. Only this is n plus 1 because this is just a column matrix. So we interested to generate this one through the loop. So your loop one as it is U1, U2 define the and DU define the. So now what is the we defined dn. So here we are getting the Jacobian in the form rho by h into you will get here u1 by 3 plus u2 by 6, then u1 by 6 plus u2 by 3. You can continue or you can go for the next line. Minus u1 by 3 minus u2 by 6. And then you have the last term, u1 by 6 minus u2 by 3. So these are our dn, and this will help you to generate the Jacobian, which is you can retain as maybe Jn with element E plus 1, this is equals to same thing we just and end here, and then end the okay. So where we was, that is the Jacobian we are interested to implement here. Now we just follow the same condition as a Blasius one. That means the no slip conditions at the surface and ambient condition at the boundary layer. So let we apply these conditions. So we can say R1 is equals to U1 and J obviously that always consider as a that is always weird because initial first element we need to take from this Jacobian matrix, and obviously the last element also. So these are the conditions we can implement here. This equals to 0, but j and n should be 1. Because boundary condition at the initial point and at the end point.
So should we check over the first one? Should it be J1, colon, and
Comma,
0?
yes. I see the error is already appeared there. 1, comma, the column itself, this should be 0. Yeah. This should be 0 because we only consider the first element because the condition at the boundary. So first and last element is 1, remaining all should be 0. And then our target to now find the solution. So delta we can written as a minus j by r and our U is modified with this delta value. I think the remaining delta will go. Now, as I told that when you do these things, our main target, here we are using the both condition, either maximum iteration or maybe we can check the tolerance. So now let's put this, the condition of convergence, which is based on the tolerance. So now we'll convergence condition. We can put here. So if norm delta infinity, if this is less than our tolerance, then we can print maybe the convergence has done, or maybe convergence in some iterations. And then we can just print it with the next line. And here we can count our iteration. And then we can break and come out from the loop. So this is what our things, and we are done with the code. But obviously we are interested to display some things. So we'll go for the plot. So let we go for some let plot what we can do. Nodes that they can display all the things.
Prof, excuse.
Yes, please.
Shouldn't it be delta equal minus J backslash R?
By R. Yes.
Yes, Prof. Thank you for
Oh, sorry. It should be the opposite
Yes,
one.
Yes, Prof. Thank you.
Thank you to help me. It's good. By this, so where we were, yes, we are interested now to find the plot. So, sorry, in infinity. So this is the simple. Oh, okay, fine. And then you can put the label. Then you are interested to put the label, or it's fine. We can say the grid on so that we can see the grid, and we can end here. Okay, sorry. This end, if we define this is a function form, then we can end here. So that we define this one as function form. It is easy to save the name. So maybe let's say this is a function Glaciers with MHD. So then we can end it here after the plot. Hope we will not get any error now. So if we now we run this. Okay. Something is there, line space. Nodes, is cap 0, L, n plus 1. No, it's fine.
Prof, is it line space rather than line space?
Line space, yeah, is good. You are right. Line space, yeah. The error is everywhere like this, line space error. Okay, this is everywhere. Line space. They want, what do they want? This is sometimes a big problem. Sometimes it is running well, sometimes they are given the problem. No, it's not display. I don't know what happened. Let I show you this code. I had written somewhere this code, and I think that will be well running. Let's see. Yes, no. You can see this code, right? This is the same code what we had written here. I know sometimes it is difficult to run the things, but if you see run this one, we can see the curve like this way, right? It's the same code. Is this appear? So
Yes, sir, we can see.
So this concept, this is how you can write the code with the MATLAB. So if you see that we go for the discretization, we define the constant matrix, we assemble A and M, then we go for the initial guess, and then we go for the Newton-Raphson iteration, residual Jacobian, and then go for the conditions. And this is how we can modify our U. We check the convergence criteria, and at the end, we plot the graph. So this is the way you can use this step by step to find the solution. So let I back to here. Let I stop share from here. Then I go back here. So here you can see the code, and we had explained the things, and that is how you are getting the velocity profile. The zoom is, everything is fine. Yeah. Now we always think about because when okay, so when we are using this finite element method, we always interested to compare with the other methods how it is here and how it is when we are using the other method, how it will looks like. So if you see here, we try to compare the finite element method with the well-known BBP4C method, which is very common used to solve the boundary layer value problem. And if you see carefully that this one is for BBP4C, and this one is related to the finite element method. And we can observe that this finite element, that they are converge nicely than this BBP4C method, right? So that's why in the present, though boundary layer value problems are the simple one, but the peoples are using this finite element methods there. And if you see, when I write that the previous code, you can see in first iteration, it is directly converge in the first iteration itself. But when you are using BBP4C, you will get the more iteration to converge it. So that means it is taking time. If you see the taking time, it is take the less time for the finite element method than the general methods like BBP4C. Now, another interesting thing is that generally we told earlier also that when we try to compare with the elements, we had the linear elements, we had the quadratic elements, and we always see that if you have or go for the complex elements like that quadratic, maybe it will more finer than the general linear one. So we also interested to compare linear shape or linear elements with the quadratic element for the same problem. And we try to see that are we are getting any benefit from there, or it is the same like linear one. So quadratic shape means you have the three nodes there, right? And in that case, your shape function like that, phi1, let's say xi, and we know this is defined as 2 xi minus half, xi minus 1, right? Then second node, which is the middle node, we can say phi 2 xi. It is written as a 4 xi 1 minus xi. And then phi 3 xi, it can be written as a 2 xi into xi minus half. And accordingly, we are interested to put this, sorry, I think something is wrong there. Sorry, let I clear it. I think something is wrong there. I put. It's difficult. Okay. Let's say our quadratic elements are phi 1 xi is equals to half xi minus 1. Let's say phi 2 xi, the mid element, which is 1 minus xi square. And phi 3 xi, this the element is half xi plus 1. Right? So as usual, if you find the derivatives, because we need the derivative for the nonlinear terms and also for the other cases. So this will give you xi minus half d phi 2 d xi. This give you minus 2 xi, and d phi 3 d xi. This gives you xi plus half. So using this one with quadratic elements, now we are interested to again find those matrices. What are the matrices? The stiffness matrix, then the mass matrix or the magnetic matrix related to the magnetic parameter, and the nonlinear convection. And obviously, since it has the three nodes, that means now we expected a 3 by 3 matrix in place of 2 by 2 matrix. So I just write the things, the final form, because I know you all are familiar with the things. So stiffness matrix, this Ke, you can written as a mu by h, 1 by 3, and the elements are 7, minus 8, 1, minus 8, 16, minus 8, 1, minus 8, 7. We follow the same process. That means when we are find, we just simply integrate from minus 1 to 1 or L by L, anything. Del phi I del y, dy, then d phi j dy, and dy dxi to get the final solution, right? So this is the general way we find out these matrices. Similar way, you can find the matrix which is related to magnetic field, that is ME, and we'll get like that way sigma b naught square by 30. You can practice yourself. Maybe I think you will get the same values. 216, 2, minus 1, 2, 4. And the nonlinear convection matrix, this Ni, you can retain as a rho U3 minus U1 by H into H by 6. You will get here 2U1 plus U2, U3 plus, U1 plus U3. And then you will get 2U3 plus U2. So when you will get this matrix, then the things are easy for us. That means we can easily find out, or we can put this one, and we can able to compare the things. And what we get there when we are compared that one? Let I share here. So again, I want to share this one. I hope the matrix is visible here. So we'll go for this comparison and compare linear quadratic AFEM. So these are the comparison of these two. And when we compare this one, we observe that they basically, for the boundary layer value problem, if your geometry is simple, because here, if you remember that our geometry is simply the flow is there, which has the velocity u infinity, and we had the horizontal plane, and there you have the boundary layer. So since the geometry is very simple here, and when you have the simple geometry, in that case, you will get the linear and quadratic, they will give you the same results. And it is always better in that case, you may go through the simple one. That means what you have the, yeah, I think it is clear now. Yeah. In that case, it is better you can go because the quadratic is the time taking, right? So we'll go for the next. So here the same information is given here. How you are getting the shape function, how you are getting the elements, and then you will get the viscous term, magnetic term, and nonlinear convective term. And this is a comparison, and final comparison you will get like this way. And the convergence is better, accuracy is better, but since the geometry is simple, it will better go for the linear one. This is the reciprocal calculation. So I also try to show you the residual part. So residual basically gives you the idea, the convergence of the finite or numerical scheme, and we can see there that with the iteration, the residual is going down, and it is end with 10 to the power minus 10. So now we generally solve the simple one, that is the Blasius equations with magnetic. Now we will go for some additional item. That means the temperature equation we involve here. So if you see this one, here, this is the continuity equation. This one is the momentum equation, because this is the boundary layer problem. And this is a simple temperature equation we had considered here. So with the general one, sorry. Here we have the additional conditions is this one. TW, T at 0 is TW, and at L, this is T infinity. So the first problem, when we solve that one, we directly using that equation, and we solve that one. But in boundary layer flow, we know that there is a possibility to simplify those equations in a simple ODE form. And for that, we generally using a transformation which is called the similarity transformation. So in this problem, we are using the same concept of similarity transformation here, so that you will get more simplified form of the equations. So in the non-dimensional form, we are getting this equation. This is the first equation, momentum equation, and this one is the continuity equation. Here PR is represent the number. And as usual, we had the simple conditions like that. This is one condition which is on the velocity, and this is the condition which is on the temperature. So now in this case, our form is the simplified form. Okay, why we have the similarity transformation? Similarity transformation is useful to get the non-dimensional form of the equations. Now, non-dimensional form means, no, it is not always true that you reduce the PDEs to ODE. Even it depends on the what kind of similarity transformation you are using there. Even some cases you can observe that you get from the PDE to PDE. But only the thing is that in this similarity transformation, we are able to non-dimensionalize the equations. Even if you see in this equation, in second temperature equation, we are getting a term which is called the Prandtl number, PR. This is a non-dimensional parameter. And what is the benefit you are getting? So when you have using this PR, that means you basically put any constant value. Suppose we know that this is equals to 7 when we are considered the fluid as a water, right? Okay, second thing is that when you will go for the plots, suppose we are interested for the plot of velocity, that means the f dash with respect to eta. So in that case, f dash is go in the non-dimensional way, and most of the cases, suppose in this case, if you see, this goes to 1, right? That means you will get simply a curve like that way, f0 is 0, and then it is slowly converges to 1 like this way. And that is how the things are going on. So that's why the non-dimensional similarity transformation is important, mainly to non-dimensional the parameter, so that you will get a good, it is easy to handle the equations, and also it will give you a good observation for the graphs. So, sorry. Okay, here I. So now our target to how to using this finite element concept in this equations. And also here we try to write a code based on that, how we can accumulate both equations together. Right? As we try to solve the equation, we think about this weak formulation, then we can see the from how we implement there, right? So let's try to go for the things one by one. So what we had in our hand, our equations is f triple dash plus half f double dash is equals to 0. And also we had theta double dash plus PR f theta dash this equals to 0. I'm not going for more details here because we know already the process. So first we go for the AFEM discretization. So when we are go for the AFEM discretization, we can go for 0 and maybe some eta maximum. And our H is by default, it is depends on how many nodes you have considered. So eta maximum by, let's say we had considered here n number of, and then we can go for weak formulation. So in this, the weak formulation, we'll get here 0 to eta x, and then triple dash plus half f dash, double dash, and then v or phi, whatever you can consider, with d eta. And this one you can simplify because this is the higher order. So we try to simplify this one, the lower order, because handling higher order is sometimes very difficult. So we can say double dash plus half f dash this phi d eta. And if you integrate this one, you can simply, you get as a 0 to eta maximum f dash phi dash d eta plus half f prime phi d eta, 0 to eta maximum. And similar way, you can go for the weak formulation for the temperature one. And as I told you that since the problem is very simple, so in this case, better we can go for the linear shape or linear elements. And we know the definition of that one, where phi 1 can represent as a eta I plus 1 minus eta by h, and phi 2 can written as a eta minus eta I by h. And from there, we can generate the stiffness matrix. If you remember that, is the same way like what we had done with Blasius with the MHD. Here also we will get the same 1 by h, 1 minus 1 minus 1, 1. Here no elements for the magnetic arm, but for what is called non-linearity, ff double prime, you are getting the element like the same way. And with the same manner, we can go for the temperature one. So let I show you now the code and try to explain the things one by one so that you get a clear idea about it. So yes, I see also 1 hour 30 minutes gone. Okay. Let I am not put. This code is not visible. Is MATLAB visible there?
Yes, sir.
Okay. So you can see this is the code. Let I try to explain. So first, as usual, we are interested to put the values of the parameter. So we consider that eta maximum is 10, and we consider the 200, that means the number of elements. And according to that, we can define the size of the element. H is eta maximum by n. And here we have only non-dimensional parameters is Prandtl number, which is 7, and that is for water. And the remaining things are the same. That means eta, we can take the line space from 0 to eta maximum. And we had F, FP, FPP. So those things, we just initialize that one all as a 0. So this is the tolerance, which is 10 to the power minus 6. And we consider here the maximum iteration is 100. So basic concept or basic ideas are same here. And you can see one by one, this is the globalize the matrix with this form. And then we are put this loop where we try to find the things. We for that's if E modify is as yeah, this is the one. AFEM we solve for using the conditions here. Here we put some additional ideas. This is only for the smoothness purpose. We are using basically give the more smoothness of the things. And then you can plot the graphs. Let me just concentrate on temperature. So when you plot the graph, we can see here how it looks. Our graph is not coming, right? Stop share. Yeah, bound temperature start from 1 and it is goes to 0. So this is how you are getting the things. And we can see here, this is within 22 iteration, we are getting the convergence, complete convergence. So this is the way how you can implement the code and you are getting the results. So let I try to now complete, is almost more than 1.5 hours. So here recently we had done one work. So where we are using some complex governing equations and conditions also. If you see the boundary conditions here, the convective boundary conditions, which is Newman conditions are there. So we are using the transform and simplify the equations. And as usual, simplify the boundary conditions. And after that, using the weight residuals, and here we are using the linear shape to solve those problems. We put this convergence criteria here, this one. These are the matrix form, what we are getting, the stiffness matrix. And this is one very important part we generally use in place readings. So we'll see the number of iterations, and after that we'll decide that which one is the perfect for us, because if you increase the elements, that means you are getting or taking more time there. So that's why we go for a suitable point where you will get a good things, as well as usual. Your iteration should not be more. So that is how we choose this number of elements. And when you are getting the things, then you can easily generate the graphs. It may be in 2-dimensional form, it may be in 3-dimensional form. I can send those results in your paper. So these are the few ideas. And here I can end, because we basically know how to initially generate the code with a simple problem, and then you can extend that code for the complicated problem. And in finite element method, you just take care about 2 points. One is the, if your geometry is complex, that means where the disturbance is more, there you can take the mesh size is small one. And more elements you can consider here. But for the boundary layer value problem, most of the cases you can go for the same size of the elements, and number of elements is not that much impactful. After a certain number of elements, you will get the grid independence. And okay, let I end here. Thank you very much to listen me, and I hope you will get some idea from here. Thank you.
So any questions from the audience? Sir, there was one question from the audience that was available in the chat box.
Yes, where is the chat?
Yes. Sir, it is like, I think all the previous questions you have already answered. So dear sir, the lecture is very informative and helpful to us to understand how to solve equations using finite element method. It would be even more helpful if you share PPT and MATLAB code. That is okay. Other one, sir. Sir, can you please explain again how to define matrix 1 minus 1 minus 1 1 and 2 1 1 2 in KE and ME respectively?
I think even when I will share the notes, yes. No, this stiffness matrix, can I explain here, or maybe I can share with the notes, maybe?
Your choice, sir. Your choice, sir.
Yes. I can share the things here. Maybe I can start here. So generally the stiffness matrix, when we are defined that matrix, we mainly focus on here, we are considered the linear elements, right? This is our, let I write it. Yeah. These are the elements what we are considered here. So from here, when we will write, first we can go for the simple derivatives also we can put with us, because we are going to use these informations here. dy equals to 1 by h. So let I go for the first element. Maybe the diffusion term. If you see the diffusion term, we had the diffusion term like that, yi plus 1 mu d phi I dy d phi j dy of dy, right? So now here the elements you have phi 1 and phi 2. That means here the possibilities what you will get, your 1 1 element should be d phi 1 dy d phi 1 dy, right? This is 1 1 element. Your 1 2 element is mu d phi 1 dy d phi 2 dy, right? Then your third element is 2 1 element is d. Let's start with phi 2 dy d phi 1 dy, right? And then your fourth element is mu d phi 2 dy d phi 2 dy, right? So these are your elements are there, right? Now we can go for, if this values here, what you will get here, mu you can take common. Then d phi 1 dy, what you will get here, let's see. d phi 1 dy is minus 1 by h into minus 1 by h. Here you will get minus 1 by h, 1 by h. And like that way you will get minus 1 by h, I think 1 by h. Then minus 1 by h into minus 1 by h. And that is how you are getting mu by h square. But obviously this h you are getting because you are cancel that one there, 1h. So you will get 1 minus 1 minus 1 1 is this one, right? And similar way, you will get the mass matrix also.
Sir, one participant is asking, sir, I saw you defined the boundary layer thickness. I didn't see if you calculated it through. Did you calculate it or graph it by chance?
No, a boundary layer, it is not, you have different formula to calculate it, but here, boundary layer means that I told you that suppose some flow is there, and you can put, let's say one channel, simply the water flow through a channel, and if you put some obstacles there, let's say this one, then what happens? Here, this water generally flow like this way, but due to this plate, it has a disturbance here. And if you see, the disturbance is more in this region, but far from there, you will get the same velocity, right? So there is the way you can easily find out what is the layer thickness. But in boundary layer problem, what we are doing, suppose when we are finding the velocity profile, see, after a certain value of delta, which is basically later non-dimensional as a eta, so after that sometime you are getting the same stream value. That means you have eta is start from here, or maybe your delta is start from here, and it is from 0, and after certain time you are getting the same ambient velocity, which is your V naught. So boundary layer, when you are plot the graph, this is actually represent that where your thickness layer, suppose this is end for delta is equals to 5. That means your boundary layer here is 5, right? Because after that you are getting the same velocity, which is your free stream velocity. I don't know if I give you the correct answer.
No, sir, this is perfectly correct
answer.
Yes, Prof. Thank you for that.
Yes.
Any other question from the participants? Okay. So in the absence of questions, may I request the organizers to display the certificate? Yeah. Dear Professor Sachin sir, I really very thankful to you for giving a wonderful talk on the topic finite element method for solving boundary value problems. In your talk, the participants have gained much knowledge on various aspects, starting from defining the problem, how we can make the weak formulation, and then how we can write the coding in particularly. In that coding, each and every thing you have in detail explained, and like you have written online directly the coding. It is really amazing. That might give the clear understanding on making codes for finite element method. That is a very basic and it is very well explained. And you also given like multiple problems and the convergence analysis and all the type of analysis, even the like independent grid independent test, all the things you have explained in detail. This is a complete lecture. I hope the participants gained knowledge from your very insightful lecture. So we really thank you for this wonderful lecture. And on behalf of the organizing committee, as a token of appreciation, we would like to present this certificate to you. Thank you very much, sir.
Thank you very much. Thank you, Prof. Sivraj.